This is Constant Insecurity, Things You Didn't Know About Portable Executable File Format with Mario Vucsan and Tomislav Perichin, founders of Reversing Labs.
Hello everyone, my name is Mario Vucsan, this is Tomislav Perichin. As mentioned, we are founders of Reversing Labs. And today we have, for us very exciting, very interesting topic always, the PECOFF, format and specification. And our topic, which we called, constant insecurity, looking at things that you didn't know about, this format that has been around for about 18 years now. It's something that we got a lot of comments, as we know everything about it. What is there new? Why should this be, BlackHat, topic to begin with? And we tried giving the rough drafts to some friends, and we got some really great comments and feedback. And people were excited about the material that we'll present today. So we really hope that you'll have some hopefully good questions for us, and find some of this stuff very exciting and very unusual as things unfold. So why we call this a constant insecurity is that P is just a wonderful example of maturing code base that has been around for many years, that has seen many different mutations, many different optional features being brought in, being deprecated at a time where backward compatibility had to be maintained, where allowed values in their format have been changing from release to release. And a format that, like any other major software project, suffers from being point released, bug fixed, on and on, whereas some of the initial design premises and design points, get migrated from one developer to another, from one concept to another. So we're really looking at this, from just a holistic perspective, that this is not only the type of the stuff that we should be investigating, not only for P, but for all the other major software projects in the future. Anything that really carries multiple specification, that had some negative testing, not enough, that had even SDLC process applied to it, something that has created a fair amount of problems in the past. So what we really have looked here at was the difference between the document and the real behavior, in regards to the P format. So you got on one hand the PECOFF, documentation, the official specification, and then you have reality in terms of how things work, what is really allowed to be run under which conditions. And if you're just looking at the documentation, you'll always be behind, just like any tech writer is behind real code. And this is sort of literally, our human way of dealing with these things. It's just the way the code is written is, constant juxtaposition between the MRDs, PRDs, product management guys, software developers who take things, in a bit different manner, and then of course, the guys who have to clean up, and convert this documentation in something that describes the innate design that a particular release, had to be designed with. So what really happens is that we have inaccurate translation here, not only in language, that's sort of additional level, but just simply inaccurate translation of how we speak. The product management will speak one language, developers another, and tech writers another way when describing some common concepts. As low level as simple functions and return values. So we do have, a lot of stuff, just a lot of problems that have to deal simply with communication. But then the other one is just stuff that's in the mind, and that's your design as you envisioned it, and then how you communicated it to the person who's gonna put it into documentation. Which then makes a lot of problems for those who actually have to read, and in reverse try to figure out how a piece of code, piece of API has to work with. So these are sort of, very high level, global thoughts on how this works. nothing here that we have not seen before. But if you think about how we have gotten here, it's really that thinking of how do we go back and try to figure out what was our design 1 year, 5 years ago? How do we document our updates and bug fixes, especially security fixes, as they relate to the underlying design premises? So we really definitely have this large dichotomy between the desire to have zero bugs, to fix everything as soon as possible, and to have accurate, well-meaning documentation that prevents misunderstandings of different types. And you'll see shortly what we mean by that. Yes, again, when we get in the world of bug fixing, definitely documentation doesn't really follow with it. Doesn't get updated, modified to the point that the subsequent readers could accurately redesign the implementation. So what we're going to do today is, we're going to look at just, really briefly, what PECOFF format is, and then we're going to really go into straight into malformations, dividing them into two different types, simple and complex malformations. This is really our way how to define them. We just realized that this would be like a wonderful way to be able to segue into our research. Now, portable, executable, and common object file format, being released in 1993, has been around with us for forever, I guess. If you can, as you can say. So it has been on every single Windows OS ever since. It's a file format that targets obviously executables, any kind of object code, and DLLs, and deals with 32-bit, 64-bit of Windows operating systems. Now, its data structure encapsulates the information necessary for the Windows loader to manage the compiled executable code that has been wrapped in it. Also, it's interesting to note, there are other places where this format is used, most notably with EFI, that has been, whose time is actually coming and is being used more and more, and McAfee definitely has focused significantly on that, and we got React OS, and Wine. So back to this concept of malformation, just to get our definitions of what we mean by it. Again, divisions in simple and complex modifications. We're really talking about file format data or layout that is modified in an unusual form in such a way that boundaries that are permitted by the file format documentation are still considered valid from the standpoint of tools that parse them, which on the other hand is not the way that the Windows loader may interpret them. So the main purpose of such malformation would be really to break or omit tools from being able to parse such malformatted format correctly. So simple malformations we'll look at will require single field or data table to be modified, and complex modifications will require multiple fields or data tables to be modified. And so, what is the sort of the security implications to this? Okay, breaking stuff, breaking, unpacking systems, it's usually a big thing. Allowing remote code execution, denial of service, abilities to escape sandbox. It's one of those things, which make the PE file format very hard to properly validate. It's because it's very complex. It has many things that work in multiple ways, that could produce the same result. And backwards compatibility is sort of, I think, one of the largest elements that contributed to this sort of the multiplicity of approaches here. Having said that, we looked at what some other people have written on the topic. We're especially indebted to Peter Ferry, who gave us some really good comments and was very happy in the way the research came out, but also who is a writer on quite a few things on this topic. So having said that, I want to invite Tom to actually start looking in the detailed layout and P malformations. Hello.
My name is Tomislav Perchin. I work at the Reversing Labs Corporation, and I'm going to guide you through the more technical part of the presentation. So before we begin, if you would be so kind to raise your hand if you ever parse the PE file format so you know what the general idea is. Okay, that's perfect. Almost everyone. It's great for this track. So I'm going to tone down a bit on the basic stuff, but still we're going to have that. So this is how the portable executable file format looks on disk. So traditionally, this is the way it was documented. So the file starts with the DOS header. It's followed by the portable executable header, which consists of two parts, which is the common object file format header, which is non-optional. It's always present. And you have the optional header, which is only there for executable PE files, such as executables and dynamic link libraries. Following that, you have sections, which contain code, data, imports, exports, resources, relocations, and everything else that's needed by the application itself. And at the end of that, you have the appended data, which is considered an overlay. So this is a traditional layout. This is how the PE file format was described in the documentation. And the point of this talk is to show you why this is wrong. So we're going to start with the basic stuff. So every file starts with a DOS header, and only two fields out of all of the fields present in the DOS header are important to us. It's the first field, which marks that as an executable file. So every file starts with an MZ string, so that's just 2 bytes. And the offset free C hexadecimal, you have a 32-bit value, which is a pointer to the PE header. Now there are a couple of rules about this pointer. It always has to point to the PE header. It's a 32-bit value, which means that it ranges from 0 to the maximum amount, which is 4 gigabytes. And it has to be aligned to 4 bytes, which means that if you divide a number by 4, the remainder will be 0. So that's the DOS header. That's how every file starts. Now, only a field that is really important and the one we can modify from the DOS header is the pointer to the PE header. So if you look at the right side of the screen, you're going to see a traditional layout of the file. So nothing has been changed here. But the pointer enables us to place the PE header anywhere in the file. It doesn't have to be following the DOS header as it usually is. So it can be inside of the file, inside of the overlay of the file. And that's a totally different question, is how do you define what is overlay? So in this case, on this graph, everything actually is inside the size of headers, which means that everything inside the file is also part of the headers and part of the sections. So just by moving the PE header outside this standard location, we are able to malformat the file and affect reverse engineering and security tools, which were expecting this header to be in certain ranges from the start of the file. So that is the most basic malformation you can do. Its implications are not that severe, as it's only moving the PE header. Now, following that, it's the same idea, but we are extending on it, is the size of the optional headers. Now, I said before that the file consists, the PE header consists of 2 parts. One is the common object file format header, which is always there, and you have the thing which is called the optional header. Now, since the optional header has a variable size, it has to have a field which defines how long it is. Now, that field is a 16-bit number, which means that we can move the size of the PE header by a certain amount of value, which is 64 kilobytes. So just by extending the value of this field, we are able to move the section table, which contains all the pointers to the physical and the virtual data inside sections, to an overlay. And why is this important? If we were to move the section table to overlay, then the section table will never be mapped in memory. It will be parsed by Windows, and all of the sections will be allocated normally, and all of the data will be there, so the file will be normal, and it will execute normally under any Windows. However, the section table will not be present in memory. So if you have a tool which is parsing the memory content, it's either doing the dynamical analysis or memory analysis, it will not be able to find a section table. So it will know that there are sections, but it will not be able to find that. So we have a demo as well on this, and we're going to have multiple demos during the talk. So as I'm presenting an idea, I will just show you how that will work. So the idea is that we can have sections outside memory. So this is a simple file. It doesn't do much. It's a file that has been designed to download the file from the web and execute it. So it's meant to do just that. Now, I've just loaded the file in Oli, and as you can see, Oli cannot find the section table. So it's telling me that the file is broken. Well, in fact, it isn't. So if I went to the original entry point, you can see that all of the code is there, and I can just step through it and execute this thing. So this would just download the file from the local host and hopefully execute it. So that's how the file works. Now, if we look at the P header, in the memory dump, and I realize that this might be small, so I'm gonna adjust the font size. Should be this. No, it's not. Doesn't matter. So if you can see here, that's where the P header starts. And usually at the end of the P header, you would have a section table with the names of the sections. Now, as you can see, in memory, there's no such thing. And if we would search the entire memory of the file, we wouldn't find it. But if you look at the same file on disk, so in a hex editor, it's still not there. But if we go to the end of the file, we're going to see that that section table actually exists. But it is never mapped in memory, and that is the problem. So if I open that in a P header editor and just go to the last section, you're going to see that the last section has a physical size which ends just before the actual section table begins. So the idea is that we can commit this data and have it only on disk. So the parsing tools are not able to parse the section table. So that's one of the malformations. Now that was the size of the optional headers. The actual size of headers is the combined size of the DOS header and the P header. And it is meant to reserve memory space to hold all of the P header data. Now there's a problem with this. This works like that in theory, but in practice there are some differences between the documentation and the implementation. Documentation says that this number should be rounded up to file alignment, while in fact it isn't. It can be any number, and all up till that point is considered to be part of the header. Now that is a problem. As you can see on the screen, we have marked a certain part of the P header as the region that belongs to the headers. Following that, we have something we call the continued P header, and that is the part which will never be mapped in memory. However, it is still present on disk. And the idea is, and if you have something present on disk, then it will be parsed by tools that do statistical analysis. However, when you are loading the file, those fields will be totally irrelevant as they will not be in memory. Now, building on top of that idea, we came to conclusion that we can have two P headers. Now, so far, you heard me talk about the P header as a single element, and it usually is. However, because of the specific values that you can assign to specific fields inside a P header, you can achieve the effect of actually having two P headers, and this is quite useful. To do this, you have to do the following thing. Now, imagine that the raw size of the header is 1,200 hexadecimal bytes. Now, if the NT size of headers is set to 1,000, that means that only the first 1,000 bytes will be actually committed in memory. Everything following that will only be present on disk. Now, if the first section starts at the raw offset 1,200, so it's just continuing, but its virtual offset is 1,000, that means that the content of that first section will be written and become a part of the P header inside memory. So this way we can stitch together two pieces of information to make a single entry. So the part of the P header on disk and the part in memory, which is effectively in the first section, are in memory considered as a single entry, which is the portable executable header. Now, why is this important? Since we can cut off the part of the header, that enables us to have two bits of information, one which is valid only on disk and one which is valid in memory, and the one in memory is actually parsed by Windows. So the effect of this is, if you look at the slide, is that you can have double tables. So you can have a double import table, double relocation table, double export table, any kind of table you want. All the data on disk will be valid for statistical analysis, but that data won't be the data that's actually being used. So the thing in memory is the thing that Windows processes. So I'm going to demonstrate that with a small demo. So dual P header. If you look at the file on disk, we're going to see that I moved the P header quite a bit down, so just like in the slides. So this is the P header on disk. As you can see, it has a section table and everything. However, since I mentioned that this will be overlapped with the memory region of the first section, that means when, if you look at the data for the first section, then that's the actual data which is going to be parsed. So at the start of the first section, we have this data. As you can see, this is the continuation of the P header, followed by the section table. So you have two section tables as well. One here, which will be parsed in memory, and one at the end, which will be parsed on disk. So here is the issue. If you look at look at a file with a tool which does statistical analysis, you can see that this file only has one import, and that is the exit process API. Now, that's all fine and dandy, but if you look at the same file inside the debugger, you're going to see that not only a single API has been loaded, we have 3 APIs that have been loaded, and from different modules as well. So this is a direct result of parsing the incorrect data. Since the statistical analysis tools are parsing the data on disk, they have no idea whether or not there's a different table. So in this way, we can achieve double tables for everything. But there's a limit to what you can do with this. And the limit is what is the minimum amount of data which has to be loaded in memory and be considered part of the headers. And as it turns out, just after the file alignment field, everything else can be doubled. And now we're going to talk about file alignment. File alignment is a factor which determines where the actual section starts on disk. So if you look at the sample, it's going to have a section which starts at the offset 10. But since that's not how file alignment works, the actual section will not be read from the offset 10. It will be read from the value which is got by the calculation inside the formula that's written below. So section offset 10 divided by 200 and then multiplied by 200 will result in 0, which means that this section doesn't start at the offset 10, it actually starts at the offset 0. So that is how file alignment influences where this actual section starts. And this has been used by a packer, and the packer is called NSPack. So if you're analyzing that, you have to read data from the start of the file for the first section and not from the offset 10. Now the section alignment, there are not many malformations concerning it. However, it is important for later on, so I'm just going to mention how it works. Section alignment basically is a rounded up value for every section. So if you have a section alignment 1000 and the size of headers is 2000, that means that the first section starts at the offset 2000, not 1000. And all of the offsets for all of the virtual offsets for the starting points of the sections have to be a multiplier of section alignment. So that's the idea behind that. Now, file alignment that we just mentioned and section alignment work together. Now, I've said that the section alignment has to be a multiplier of 1000 because that is the default value for the platform. However, it can be lower than that. And if you have values for section alignment and file alignment which are the same, so for example 200, then the portable executable header will magically become writable to you. And this is a problem because normally portable executable header is considered read-only and executable, but if the data execution prevention has been turned on, then the section headers are only read-only. But having headers writable is something which is very, very useful for tricks that we're going to use later on. So I also have a demo for this, and it's a short one. So the writable headers. So idea is simple. We set those values as said before, and this will just update the first 2 bytes of the file with an MZ signature. This has a potential of breaking sandboxes because usually section headers are not something you want to write to. So as you can see, we've successfully executed the first command, so we updated the first 2 bytes to the same value, and then the code can execute normally. So this is really simple. You just set the file alignment and section alignment to the same number, which is 200 in this case. Now the address of entry point, as we said, sections consists of code, data, and imports, but for Windows to know where to start the execution process, it has to have an address where the actual execution process starts. And that's called the address of the entry point. Now the address of the entry point, as implied by the documentation, should reside inside the boundaries of the file. However, that is not the case. If we have address of entry point set to 0, that is usually reserved only for dynamic link libraries which have no entry point. However, if you were to do that for an executable, you would end up executing the code from the first 2 bytes. And the first 2 bytes are always the same. As we know, that's MZ. Now, MZ disassembled is decrement EBP and then pop EDX. After that, we can just take over control and continue executing from any point in the file. Now, that is if the address of the entry point is set to 0. However, address of the entry point can be set to any number, and that number can be used to point to something that is loaded outside the file. So for example, if your application is statically loading a dynamic link library and you know where that dynamic link library is going to be loaded on, you can set the entry point in your executable to point to the statically loaded dynamic link library. So the code would actually not start executing inside the file, it will be starting its execution in a dynamic link library. And this is possible because there are no boundary checks in the PE file format. So you can have all sorts of fields which are actually pointing outside the file, and the address of the entry point is just one of those examples. And this is useful because if you are trying to break, for example, dynamic unpackers. Dynamic unpackers usually use the address of the entry point to set that breakpoint. Now, depending on the time when that breakpoint is set, they can either mismatch that breakpoint or just consider the file to be non-valid because the entry point is not in the file. Now, the section data. Sections consist of data which is loaded into memory. However, if you look at the file on the right, if we imagine that that file is 3,000 hexadecimal bytes, then we have an option of splitting that section into multiple parts. If we split that section in multiple parts and still hold on to the virtual order of loading those sections, so the first section starts at, let's say, 1,000, the second one at 2, and the last one at 3, we can utilize that by rearranging the data on disk. So the data on disk is no longer continual, but it is continual in memory as Windows will load it the correct way. And why is this a problem? Well, if you are writing static unpackers and you want to unpack the content, you would usually read that from disk. Now, if you are unaware of this technique that we call the section data shuffling, then you would just read that data from start to end. Now, the problem with this is since the data has been shuffled, the compressed stream has been broken, and your decompression will not work. The only way to actually decompress this data correctly is to simulate the loading of the file, so all of the sections are loaded the correct way. I have a sample for this. So this is a UPX-backed file, and if we look at the sections, you're going to see that the section 1, which actually contains all of the compressed data for UPX, has been split into multiple parts. And those multiple parts are present on disk, but as I said before, they are shuffled. Now, if I were to try a static unpacker for this would fail because the data has been shuffled around. But if I were to load this file inside a debugger, you would see that it will load normally, and I can actually just execute that to the entry point without a problem. So this is the entry point of the file. Now, this is possible because Windows itself is rearranging the data in memory, and only the data in memory is actually the one that counts. Now, we've just talked about sections and how you can split them into multiple parts. However, the next question we have to ask ourselves is just how many sections can there be in a file? Well, if you look at the documentation says that it can range from 1, so that there should be at least 1, and it ranges up to 96 possible sections. However, this limit has been removed by the operating system loader inside Windows Vista, so the actual maximum amount of sections is the one defined by the size of the field, so that's 16 bits or 64 kilobytes. So that's a lot of sections, and that has a huge impact on security tools which are not prepared to deal with that much data. Now, a huge number of sections is obviously a problem. However, no sections is a bigger problem. And there can be a file which has no sections, which is something that is counterintuitive because you would want to have sections. Sections are useful because they contain data, code, and imports and stuff like that. But contrary to that, you can create a file which actually has no sections, which means that all the data is part of the headers. To do this, we have to convert the file. And to convert this file, you have to make it so that the virtual addresses or the relative virtual addresses are equivalent to their physical counterparts. So the actual conversion between those two is really, really simple. Now, you remove the section table entirely because you don't need it. You're going to have section number 0. And you set the size of headers to the actual physical size of the file because everything is inside headers now. And the size of image is, of course, equal to the size of headers. And of course, we set file alignment and section alignment to the same value, which is 200, just to make sure that the actual headers are writable. Now, if you look at the sample, which is called sectionless, you're going to see that the number of sections is 0. And if I look at the sections, there are no sections. If I look at the file, the actual file is really, really small, but it does the same thing as before. It connects to the internet, downloads the file, and executes it. So it's a really, really small file. Now, if I were to load this in Ollie, you would see that that file would work out fine. However, Ollie doesn't agree with me. So it actually starts at the offset 0, and then you jump over to the actual code, which is executed. And as you can see, the import table has been properly filled, and you can just execute those functions. So you can have a file which has no sections. And that brings us to complex malformations. And complex malformations are the ones that require more things to be modified for them to work. So not just simple tricks around modifying certain fields. It's actually linking together data tables to work together to assure the malformation to work correctly. So for example, if we start with the import table, and as most of you know how the import table looks like, I'm just going to briefly remind you. So the P header points to the import directory table, which consists of the import lookup table and the import name table. And all of those tables working together are actually responsible of loading the necessary dependencies, such as dynamic link libraries, and finding functions inside them. So, but if you look at the import table and how it looks like, you can see that the import table directory consists of multiple fields. And some of those fields are more important than others. So dynamic link library name always points to a string, which is the name of the dynamic link library to be loaded. And the import address table points to an array, which actually points to the names of the functions or the ordinal numbers which are to be loaded. However, if the import address table is pointing to a single 0 entry, which means that that first entry marked by hint plus name is actually 0, then the dynamic link library will never be loaded, which means that you can have import tables which import any kind of dynamic link library which is not present on the system, and the operating system loader will not have a problem with that because it will never load them. But if you're creating a tool which actually parses the import table, you might think that that dynamic link library is necessary and that that file will not execute on your system. So the problem with this is that you have to parse the import address table first to figure out whether or not that dynamic link library will be loaded. And this is a simple way of breaking security and reverse engineering tools because they might think that dynamic link libraries are not there. The export table, and we're moving away from the import table so quickly because all of the tricks that follow are actually working together. So the import and the export table are working together to create a single malformation. So the export table, the idea is if you have a dynamic link library, and this is the most basic example, it can have exports. And those exports are the functions which are actually present in functions or variables which are actually present inside a file. So other applications might utilize those dynamic link libraries and call the appropriate functions. Now they can, those functions can be located by either the name or the ordinal number or stuff like that. So how can we utilize the import table and the export table to achieve this malformation? So if we start with the most simple example, if you imagine that you have a PE file, which is an executable, and it has both tables. So it has an import and an export table, but it is actually importing stuff from itself. So its import table is linking to itself. So this sample exe is importing a function 1 from its own export table. Now that function 1 can in turn be a forwarder function, which actually forwards this function to the kernel 32 load library. So this way you can obfuscate imports because you're still importing from yourself, so all of the function names are valid, but those functions are not present in the file. They are forwarded from a third-party DLL, which is in this case a system DLL, which is kernel 32. So if you were to look at the import table for this file, you would see that it is importing stuff from itself, but you wouldn't know what it actually does. So if you look at the example for that, that should be this one. So as you can see, it has two tables. It has the export table, which has all sorts of different names, and it has an import table, which is the wrong sample. This is the right one. So it still has two tables. So the export table, which has functions called redirects, and those redirects are just forwarders to the actual API. So this first one, I believe, is forwarded to kernel 32 exit process. And if you look at the import table, you're going to see that it's only importing stuff from an executable, and that's the name of the executable. So this file has to be named sample.exe for this to work. Now, this is also a problem because if you are storing malware, you're usually going to store it with a name which is like a hash or something like that. So the original name of the file will be forever lost. So if you were to load this in a sandbox, it has to have the same name in order for this sample to work. So since the name has been lost, there is no way that this sample can execute. So this is also a protection feature against reverse engineering. So as I said, it has three imports, and they're all importing from itself. So the name of the sample is different from sample, so I have to rename it to show you how it works. So now if I go to the sample, and I open it in a debugger, you're going to see this, that the import table is still valid, but since OllyDbg knows the addresses of the forwarders, you can see all of the functions being actually loaded. However, if you can see what it is actually trying to load, you're going to see that the function being called is the one being redirected. So you have the redirect functions and then numbers which indicate which one of those it is. So the first one is actually exit process, the second one download file, and the third one execute. So this is a simple yet effective way of obfuscating import tables. However, as you've seen just now, all of the imports and exports have been strings. That doesn't have to be the case. That is nowhere specified in the documentation, because in the documentation it says that the strings and quotation marks around strings are being matched by binary matches, which means that the actual data which represents the string can be non-printable data. So you have to take that into account as well when you're building your tools, because function names might not be printable, and that can also break your database or whatnot. Now the next one is building upon this idea, but it's a bit more complex. Now, still you have two tables. However, if you can see on the slides, all of the functions have the same name, which is also a problem. How the program differentiates between those two names is by hint. Now, hint is a thing inside the import table which is not commonly used. And as documented in the PECOFF documentation, it says, if you're importing something from a dynamic link library, the first entry to be checked is the one at the hint location. So the hint is actually an index inside the export table. As you can see here, function 1 has two indexes. So the first one is the index 0. So since function 1 name matches the function 1 name at index 0, then that function is being redirected to something else. The same goes to the second entry, but still it is not looking at the first entry, which is also function 1. It's looking at the second entry at index 1. So even though the names are the same, the functions are not. So if you built a tool which does your own get-proc address for this file, you would have to take into account the hint as well. And if you didn't, you will end up with the array of same functions, and that is not the case. And I believe I have a sample for that. So this hello world application, if I load it inside the Lord P, you're going to see that it imports a couple of entries. It imports the hello DLL1 and hello DLL2. However, those two functions are the same. So from hello DLL1, it imports the function hello from DLL1. As you can see, it has a hint 1, which means that the function being called from that DLL is the one at the index 1. So if I look at that file, I'm going to see the following thing. It has two exports, and they have the same name. So depending on the hint is which one of those functions is going to get called. So if I start the application, you're going to see a text message. It says, welcome to my universe, and it has an exclamation point. And then the second one, leaving so soon, was it something we said. If I were to change this dynamic link library, this executable, and just change the hint value. So if I say, okay, call the offset 0, which is the default value for hint, then you're going to see different messages. Still, it's the same name. It's just a different message. It says, welcome to my universe, but it didn't have an exclamation point at the end. It has 3 dots, which means that it's a different function. And here as well, instead of the exclamation point at the end, we have a question mark, which means that it is a different function being called. Why this was so subtle is to show that you have to look at the hint as well, because the function names are the same. One more thing about imports and exports is that you can overlap two different import image descriptors. So they are still pointing to the same import address table, but in the first pass, all of the entries from the sample.exe are going to be loaded. So you're loading the functions from yourself. And those functions don't have to be a valid function pointers. You can have any kind of data you like there, because there are no boundary checks in the PE file format. So you can use the export table to rewrite this image import descriptor to have it to point to something else. So since you are in the first try, you're importing stuff from your own executable, and in the second try, you're using the same array, but you're importing stuff from the kernel 32, that same image import descriptor has two meanings. One for the first pass, where it's importing stuff from itself, and one for the second pass, where it's actually loading stuff from the kernel 32 DLL. Now, it's the same concept as I just described, but you can use the export in the import table to actually reconstruct code. And the idea is the same. If you replace a bit of code from the portable executable with the import table, and you have the import table import data from itself, then that data will be written at the same location. And since there is no boundary checks, then you can use the export table to reconstruct code. And this might sound confusing, but if you look at the file called this, you're going to see that its import table imports a lot of stuff, but at the end it imports a lot of functions from itself. Now those functions actually are pointing nowhere in the file. They actually consist of code. So if you look at the export table, you're going to see all sorts of errors, because this right here, which should be a pointer to the actual function, is not a function. It's a code which will be written at the original location. So as we said, the file has to have the same name because it's importing from itself. If you look at the file in a hex editor, and if we go to the first section offset, which is right here, you're going to see this. And this is the import table. Here, when the file is loaded, the original code will be restored. So if I were to load this inside OLEDBG, you're going to see this. Now, the Oli hasn't analyzed this yet, so this looks like junk. But if I remove analysis, you're going to see that this becomes code. And at this particular location, you didn't have code before. You had an import table. But since you're importing data from yourself, then you can reconstruct this code easily. And you can apply this to any kind of file. And to be able to scan this file and look for malicious code and whatnot, you actually have to simulate the loading process. And that's the actual problem with this. So I'm going to restore this. So the TLS table. As you all know, the thread local storage table is used to have an automated way of storing multiple values for the same variable, and those values are specific for a specific thread. So multiple threads can share a variable, but different threads can have a different value for the same variable. However, that's not the interesting part about the TLS table. That's something you can't really mess with. The thing you can mess with is the TLS callback array. And TLS callbacks are function pointers which are actually executed before and after your application starts. But there's a cool thing about them. The cool thing is if you have a TLS table and it has a single callback, then that single callback can be used to add more callbacks, which means that this TLS callback array is dynamic and you can influence it any way you like from the execution point. So when you start the file, you can start the file with one TLS callback, and the first callback can add more callbacks. So in a way, to analyze this file correctly, you have to analyze it dynamically, because statically you will never know whether or not there are more callbacks. So if you look at the example, and that should be TLS self-extend. Just a second. I actually have to break before they execute so you can see it. So I'm going to break it in load library. And then load the sample, which should leave me at the load library. And then I can just go to the code and show you that the following thing will be called. So if you can see here, then this bit of code is actually used to write to the end of the TLS callback array. As you can see, this is the first entry, and then we're going to dynamically add a second entry. So if I were to execute this, then you can see that this memory changes, and this is the address which will be executed. And if we just go there and see what's at that address, then we're going to see the code which actually gets executed from the second callback. And from the second callback, we just have a jump to this code here, which is actually just the code which does the same thing as before, downloads and executes file from the web. So this will be executed, and this has been added dynamically. So here we have that code, and then all of the white things will be executed as well. So you are dynamically extending the TLS callback array. As before, just like before, we can overlap the TLS callback array with any kind of information we want. So we can override the TLS callback, overlap the TLS callback array with the import table. And since you're importing stuff from either yourself or a dynamic link library, those functions will be called because, yet again, there are no boundary checks. So if a TLS callback points to, let's say, load library, then the load library will be called. And the cool thing about this is that since we are calling an API, and that API takes parameters, and the first parameter for the load library is a pointer to a string. Now the TLS callbacks have a specific way that they are defined, and the first parameter will be the image base of the file. So in a way, when you are calling the load library in this direct way, you will always be loading the file called mz.dll, since the mz is the first string at the beginning of the file. So just by overlapping the import table with the TLS callback array, you can load predefined files. Now the relocation table, it is used to help the loader relocate image. So if you have a dynamic link library and that dynamic link library can be loaded on more than one base address, then you have to have a relocation table address, which enables the loader to relocate it for the address that it has been loaded on. But here's the idea. You can actually encrypt the entire file with the relocation table. However, this is really, really tricky. You can't just do that normally. You have to have some conditions that apply to this. To have this file decrypt itself and effectively decrypt all the code, data, and imports, you have to set its image base to 0. And this is really important. If we set the image base to 0, then this file on the versions of Windows before Windows 7 Service Pack 1 will always be loaded on the image base, which we know. And this is important because since we want to decrypt the file, the actual encryption and decryption keys have to be the same. So we have to trick Windows into loading this file and doing the relocation process, which will actually do the decryption. But for it to be successful, the starting point, so the file on disk, and the loaded file have to be always loaded on the same addresses. Now, if the image base is 0, this file will always be loaded on the predefined address. However, since the Service Pack 1, this has been fixed, and if you set the image base to 0, then your file will not load. However, if you don't set the image base to 0, and if you set it to the kernel address, so for example, 8 and then all zeros, which is usually in kernel, it doesn't have to be, then your file will always be loaded at the same base address. So the same trick still works, it's just a different value for the image base. Now, how do the relocations actually do decryption? Every single byte is encrypted. For the decryption process to work, you have to do it in reverse because you are actually relocating all of the data. So if you relocate the first byte in the encryption process and then all the following bytes, when you are doing the decryption part, you have to do the same section but from reverse. So this is really scary because you can actually encrypt everything inside a file. And if you're doing statistical analysis and if you don't know where this file is meant to be loaded, then you will end up looking at junk. It is only with dynamic analysis that you can see this. And the scary thing about this is that there's a malware which is called LeRock, and it has been spotted last year, which is actually using this technique. And this is really, really difficult to analyze because for you to know that this is a valid file, you have to know where it will be loaded on. So I have a sample for this, and the sample is called relocation. And if I just load the file dynamically, you're going to see all of this junk data. That's because Ollie hasn't been good at analyzing stuff. So if we remove the analysis, you're going to see that all of the code works just fine. And if I start the application, it's just a simple hello world application that we compiled. Now, if you look at the same file on disk, you're going to see that the first section is actually encrypted. So the data for the first section is actually encrypted, and the decryption process is done by Windows itself. Now, if you look at the relocation table, you're going to see why how the actual decryption process is done. So as I said, you have to do this in reverse. So the highest point is 7,000, and then we move on down to the 1,000 region. And we repeat this 4 times because we are encrypting every byte of the file. Of course, we can encrypt every D word, but to increase the entropy of the file, we wanted to encrypt every byte. And that's why we have 4 same relocations, which are actually executing one after another. So only when all of the relocation is done, the file is decrypted correctly in memory. And that's all of the cool malformations that we have. All of the rest are being described in the white paper. It's on your CDs. So how do you detect those? It's really a difficult question. Now, we divided this into sections, of course. For headers, we have to disallow files which have headers outside NT size of headers. We have to disallow files which have too big NT size of optional headers. We have to disallow files which have N2 points outside the file. So these are all the obvious choices that you can implement in your tools. Sections, we have to disallow files with 0 sections because there's absolutely no reason why such files should exist. Imports, we have to do string validation. So if something isn't a string, then that's obviously been malformatted. And we have to disallow table overlap and reuse. For exports, we have to disallow the files which have multiple entries with the same name because that's not something you would find normally in a PE file. And we have to disallow entries which have invalid function addresses because that can be used to reconstruct code. Relocations, we can analyze the entropy of relocations or just block files which use more than 1 relocations per the address block. And TLS callbacks as well. We can disallow ones that have TLS callbacks outside the image. So final thoughts on this is that P is riddled with possibilities for malformations, and you can't always predict them. So you have to design your tools as best as you can. Malformations can lead to serious consequences, such as application crashes, buffer, and integer overflows. And everyone's implementing their own PE parsers, which makes it impossible to test whether or not a certain product has been affected by a specific malformation, and if so, by which one. That's why we have created a unified document, which is published by us, and it is available at our website. We will do our best to maintain it as we find no new malformations. And we hope that you guys can contribute as well if you know something that we don't. And that's it for this. How about questions?
I saw an example of a PE file where the PE header was overlaid with the DOS header.
Okay.
Very cleverly fixed that alpha news so that would point back and it would still work.
Yep.
Did you see that or see any advantage to doing something like that?
Well, there's no advantages to that, but there are packers that actually use that. The advantage is if you are designing a software compression, then you have a smaller file. So you can say that that is a legitimate use of that.
So the PE format is basically dangerously crusty with old particles of updates and things.
Yep.
Can we just get rid of it?
Well, we can't because, as you heard from Mario, PE format is used everywhere. So if you go to an ATM, it's used there. If you play Xbox, it's used there. It's used in your BIOS. So it's used pretty much everywhere. And it's pretty old. So it's 18 years old by now, and we can't just eliminate it. Yes? Yeah, well, there can be a bad impact. However, we designed this list to keep in mind all of the possible legitimate uses of malformations. So packers wouldn't be affected by this. Yes?
So in a small back array, when you have the first entry that has new entries, how many entries can you add to affect the response space?
You can add as much as you like. It's dynamic, so any value is fine.
Will that eventually disrupt your offsets?
Well, depending on how many space you reserve for that. But I'm thinking you don't need more than a couple. Anybody else? No?
Do you have any expansion on thoughts of using PE header malformation
Things we mentioned so far can be used to do that. It depends on the sandbox design. So if you have a user mode sandbox, which just bundles around the API and stuff, if you have code which executes outside the file, then you have a potential of breaking out of it. So that's the idea. But if you have a full-blown sandbox which emulates the entire environment, then the danger is minimal.
So all of the detection methods you were talking about, is there any software that you know of that does that kind of thing?
We have our tool called Titan Engine, and it does validation of files. So some of these are already covered. However, until the end of the year, we will issue an update which will cover all of these. So it's going to be an open source tool you can look at.
I did check whether or not you can set the TLS callback to outside of the file also.
Yes, you can. So I mentioned that you can set it to a load library, and then you will end up loading the mz.dll. Anybody else? You? Last question.
The kernel mode implementation of a loader, the kernel module loader,
Okay.
be a little less tolerant to all this.
You can't, because there are really old compilers which still need to work with Windows. So if you are aware of, let's say, Watcom C++ compiler, it does all sorts of crazy stuff, and Microsoft still has to support that. So you can't just blacklist stuff as we defined it from the kernel standpoint. So this is more for security tools as guidelines of what you can blacklist and hopefully not damage all sorts of things. I think that's that. Thank you very much, guys.